We've all encountered complex numbers while studying quadratic equations which have no solutions. For example, if I have a quadratic equation x squared plus 2x plus 5 equals to 0. So our introduction to complex numbers happens when we try to find solutions to this quadratic equations using the formula method. But actually complex numbers were firstly introduced while finding the solutions to reduced cubic equations. While finding the roots or the solution to reduced cubic equations. Okay. But we'll start by introducing complex numbers from quadratic equations point of view because that is much easier to understand. Okay, so if I have this quadratic equation, I'll find the solutions using formula method. So I get x is equal to minus 2 plus minus root of b squared minus 4ac upon 2. So which gives me minus 2 plus minus 4 minus 20. So 4 minus 20 is root of minus 16 upon 2. Now we'll put a definition of iota, which is square root of minus 1. So root of minus 16 can be written as root of minus 1 into root 16, and root 16 is 4. So we'll replace this by iota and this with 4. So I get 4i. So x equals minus 2 plus minus 4i over 2, and x equals minus 1 plus minus 2i. So in this case, the two roots of my quadratic equation are x is equal to minus 1 plus 2i and minus 1 minus 2i. So when there's a quadratic with real coefficients, in this case, my coefficients are 1, 2, and 5. So in this case, the complex both the solutions are complex numbers. So I get minus 1 plus 2i and minus 1 minus 2i. We'll study this more in detail when we study polynomials, complex numbers involved in polynomials. So firstly, we'll give a definition of what a complex number is. So a complex number is any number which can be written in the form of a plus bi, where a is called the real part and b is called the imaginary part. The notation for a complex number is usually represented by small z like this. So if I say z equals a plus bi, rez or the real part of z is a and the imaginary part of z is b. Okay. Now one more thing, which is a small thing but has to be understood, is the properties of I. Properties of I. Okay. So I is square root of minus 1. So if I have to find I squared, I just have to square this root of minus 1, which will give me minus 1. I cubed will be I squared into I, which is minus I. And I raised to 4 is the square of I squared, which is 1. I raised to 5 will be I raised to 4 into I, which is I raised to 6 is I raised to 4 into I squared, which is the same as I squared, which is minus 1. Similarly, I raised to 7 is minus I raised to 8 is 1. So you can see the pattern repeats in cycles of 4. If I have to find I raised to 64, I need no further calculations. I can simply say it's a multiple of 4, so the answer is 1. If I have to evaluate I raised to 73, so I have to find the closest multiple of 4 to 73. Towards the lower side, which is 72. So I get I raised to 72 into I, which will give me I again, because I raised to 72 is 1. Okay, so next thing, operations involving complex numbers. So the most basic of the operations is addition and subtraction. So if I have a complex number z1, which is a1 plus ib1, and complex number z2, which is a2 plus ib2. So if I have to add the complex numbers, the procedure is quite simple. I'll just have to add the real parts together and the imaginary ones together, like this. So one thing which I can conclude is that for z1 and z2, the real part is a1 plus a2. Similarly, the imaginary part is b1 plus b2. No difference for subtraction. If I subtract z1 and z2, I'll get a1 minus a2 plus I times b1 minus b2. And similarly, we can conclude the similar statements here regarding the real and imaginary part. Okay. Next is multiplication. So multiplication of complex numbers, nothing different. if I have a complex number a1 plus ib1 and another complex number a2 plus ib2. And if I multiply the complex numbers, it'll follow the mainstream expansion pattern. I'll have to multiply a1 with both the terms here in the second bracket. Similarly, ib1 with both the terms in the second bracket. So that gives me in total 4 terms. a1 plus a2 plus I times a1 b2 plus I b1 a2 plus I squared times b1 b2. Now, whenever we're doing any operations on complex numbers, the resultant expression has to be a complex number itself. So the real and imaginary parts have to be segregated properly. So the thing is, in the second line, I can see this I squared term here. So this I squared, I can just replace it with 1. So I'll get a1 a2 minus b1 b2 plus I times a1 b2 minus b1 a2. So the real and imaginary parts are visible separately here. Real, imaginary. Okay, so these are basic operations with complex numbers. And obviously, when we've done multiplication, the next step which we'll do is called division. Okay, so z1 equals a1 plus ib1. Again, the same thing, z2 is equal to a2 plus ib2. So if I have to divide the two complex numbers, so I'll get z1 over z2 equals a1 plus ib1 upon a2 plus ib2. Now I've told you whenever I do any operation on two complex numbers, the resultant answer has to be a complex number itself. But the problem here is in the denominator, I'll have an I present here. So to get rid of this I make use of the concept called conjugate. So if I have a complex number a plus ib, the conjugate or the z star of the complex number or z bar of the complex number is defined as a minus ib. Basically, the real part remains the same and the imaginary part changes sign. So one special thing about the conjugate is that if I multiply a complex number with its conjugate, I'll get a plus ib into a minus ib. Now this expansion is pretty straightforward because it's of the form a plus b, a minus b, which gives you a squared minus b squared, which will give me a squared plus b squared, which is nothing but, okay, modulus I'll introduce later. So yeah, here in the denominator, what I'll do is I'll do kind of a rationalization step. In the denominator, I'll multiply with the conjugate a2 minus ib2, and similarly in the numerator as well, a2 minus ib2. Now in the numerator, I'll do the simplification by expansion. So a1 will get multiplied with a2 and a1 with ib2, and similarly the other two as well. So I get a1 a2, let's change the color here. Yeah, so I get a1 a2 minus I a1 b2 plus I b1 a2 minus I squared b1 b2. And in the denominator, since I'm multiplying a complex number with its conjugate, I'll get a2 square plus b2 square, which gives me a1 a2 I squared is minus 1, so minus minus plus, so a1 a2 b1 b2 plus I times b1 a2 minus a1 b2, and the whole thing divided by this, so I can just divide it separately here. Square plus a2 square plus b2 square. So now it's pretty obvious that this is the real part and this is the imaginary part here. So this is how you do division of complex numbers. Next thing is equality of complex numbers. We'll try to understand what are the conditions such that the two complex numbers are equal. And the conditions aren't that difficult to figure out. So if I have a complex number z, which is a plus ib, and another complex number w, which is c plus id, and if I put a condition that z is equal to w, so z is equal to w implies two equalities. Firstly, if two complex numbers are equal, the real parts are the same. That means the real part of z is equal to the real part of w, which means a equals c, and also the imaginary parts are equal. That means imaginary part of z equals imaginary part of w, which is b equals to d. So for two complex numbers to be equal, both their real and imaginary parts have to be the same. For the question given below, they're asking find the real values x and y, given that 3 minus 2y into x plus iy equals 12 minus 5y. So given that the left hand side equals the right hand side, they're asking us to find the values of x and y. So if I have to find values of x and y, that means I need two equations. So to make two equations, I need two conditions. And what I'll do is, the thought process has to be to simplify the expression on the left hand side, make it a single complex number of the form a plus ib, and then equate the real part with 12 and the imaginary part with minus 5. And this is something which we'll actually do. So firstly, considering the left hand side, it's 3 minus 2i into x plus iy. Again, doing a 4-step expansion, which leads to 3x plus I 3y minus 2xi plus 2y. I'm just writing the steps directly because I into minus I is minus I squared, which is plus 1. So considering the real and imaginary part, so 3x plus 2y is the real part, plus I times 3y minus 2x, which is the imaginary part here. Now, if the two complex numbers are equal, that means the two conditions can be brought by equating the real and the imaginary parts separately. So if I equate the real parts, I'll get 3x plus 2y equals 12. And equating the imaginary parts, I'll get minus 2x plus 3y equals to minus 5. Now to solve this equation, I can use elimination, substitution, any method, but elimination method seems the easier one. So I'll multiply the first equation with 2. I'll get 6x plus 4y equals 24. And multiplying the second equation with 3, which gives me minus 6x plus 9y minus 15. And then I'll add both the equations. So if I add both the equations, I'll get 13y equals 9. So y equals 9 over 13. And to find x, I'll substitute y in either of the equations. So I'll put it in the first equation. So I'll get 3 times x plus 2 times 9 over 13 equals 12. So 3x equals 12 minus 19 to 38 over 13. So 9 to 18, sorry. 12 minus 18 over 13. So 3x equals 12 into 13, which is 144 plus 12, which is 156. So 156 minus 18 over 13. So 3x equals 156 minus 20 is 146, 136. So this is 138 over 13. And x equals 138 over 13 into 3. But the thing is 138 is divisible by 3. So I'll write 3 ones are and 3 fours are 12, then 3 6 are 18. So I'll get x equals 46 over 13 and y equals 9 over 13.